Okay, number 54 was kind of a mess on the board today. Let me show you what Tsokos had in mind when he wrote the question. This phrasing of convince yourself is odd to see in a physics problem. And the reason that he wrote it like this is because, as you saw in my attempt on the board, it gets pretty out of hand when you try to actually find the specific direction of the 4 and 6 Newton forces that are needed to balance this object. So let's say that 9 Newton force is to the right. We know that the 4 and the 6 Newton force can't be in the same direction as the 9 Newton force, because how could it possibly be balanced if that were true? There's going to be a definite rightward net force here. So that's absurd. It can't be that. And we know that 4 and 6 can't be pointing both up, because then there's an upwards force, and these still aren't doing anything about the rightwards force. Well, what about 4 up and 6 down? Now it's worse, because not only is the horizontal unbalanced, now the vertical is also unbalanced. So I think if you think about this problem for any amount of time, you pretty quickly realize that the 4 Newton force and the 6 Newton force need to both have horizontal components that are opposite the 9, like this, and then their vertical components will cancel each other out. So this vertical component of the 4 Newton force needs to be the same size as that vertical component of the 6 Newton force to make sure that there's no net vertical force up or down, because we want this thing to be in equilibrium, which is net force is 0. The other thing that needs to be true is that horizontal component of the 4 Newton force and that horizontal component of the 6 Newton force, they need to add together to give you 9 newtons, so that the horizontal net force is 0. So if we call this, let's say, F1 and F2. The magnitude of F2 is 4 newtons. The magnitude of F1 is 6 newtons. F1x plus F2x has to be 9. That's the horizontal components canceling out the 9 newtons. Now I could also write down that the vertical components need to be the same size as each other. I know they're in opposite directions, so F1y needs to be the same size as F2y. These two things are possible. I just don't know what angles would make them possible. But I know that they can happen. So if that's theta 2 and that's theta 1, I could find some theta 1 and 2 where the vertical components cancel and the horizontal components add to 9. How do I know that I can do that? Well, what if both of those angles were 0? I would have a 4 Newton force to the left, I would have a 6 Newton force to the left, and I'd still have that 9 Newton force to the right. The total force to the left is 10. That guarantees, the fact that that's bigger than 9 guarantees that I can take some part of 4 and some part of 6 when these angles aren't 0 and get them to add up to 9, if I just knew the right angles. So Tsokos is okay with you stopping at that point and saying, okay, I realize there are some angles where this would work and I could balance the 9 Newton force. In class, this is where I went on my big detour of trying to actually find the angles, which I did after class was over, and I'll show you in a second, but I know you don't care about that. To solve this problem, the next part is pretty much like Braden was telling me to do in class. If I have it balanced, then I know that the horizontal components are They add up to be 9, because that's how I balanced it in the first place. Well, if I remove the 9 Newton force altogether from the scenario, I still know F1x plus F2x. That's still 9 because I didn't move or change the 4 and the 6 Newton force. So the net force in the x direction is still 9 newtons. It's to the left, however you define positive and negative, but it's still 9 newtons because I did not change 4 and 6. So, and the vertical components are still canceling each other out because I did not change the 4 and the 6 Newton force. So I can just use Newton's second law. I know that it's 9 newtons to the left. The mass is 3 kilograms. Find the acceleration. What is it? It's 3 meters per second squared to the left. Yes, it is that simple. Now, if you care not at all about figuring out what theta 1 and theta 2 are, which the question doesn't actually ask you to do, you can stop watching here. If you want to see the end of the rabbit hole that I was going down in class, keep watching. So I converted these to actual components using some angles. And if we say F1 is the 6 Newton force, and the horizontal component is 6 times the cosine of theta 1. F2 is the 4 Newton force, and the horizontal component is 4 times the cosine of theta 2. Those things add up to be 9. The vertical components are 6 sine theta 1, and that has to equal 4 sine theta 2. Now the troublesome thing here is that the 2 variables I want, I have 2 equations and 2 unknowns. That's usually a good thing. The 2 variables I want, however, are buried inside of cosine and sine. So it's a little bit harder than usual to just use substitution. Like if I tried to use substitution, I would get 4 divided by 6 sine theta 2, but I'd have to take the sine inverse to get theta 1 by itself. Like, okay, I mean, I guess I see what theta is. Can I plug that into the other equation? You end up with this, 6 times the cosine of this mess right here. And it just gets out of hand. Like, I'll write it, but this is going nowhere. 4 over 6 sine of theta 2 plus. So I actually have 4 cosine theta 2 equals 9. I actually have gotten it down to one equation with one unknown, but it's pretty difficult to solve this analytically. I'm not saying it's impossible. Yes, you can solve this analytically. Off the top of my head, I can't do it. I'd have to go look up some things to figure it out. But when you find yourself solving for angles in equations like this, a handy trick is stop trying to analytically solve it and graph it. Do something numerical to make your life easier. We have computers now that can graph things for us. So I'm going to erase all that. And I'm thinking about Desmos. If I could get a graph of each of these equations on Desmos and see where they intersect, then I have solved this system of equations. And Desmos wants me to graph things in terms of y and x, so I'll call theta 1 y and theta 2 x. If I solve this first one for y, it will let me graph it. I need to be able to write it like that to graph it on Desmos. So 9 minus 4 cosine theta 2 divided by 6 equals, let me write that as y cosine inverse. Theta 2 is x. So all I did really was solve this for theta 1. Then I changed theta 1 to y and theta 2 to x so I can graph it on Desmos. Do the same thing with this one. That's y, that's x. Solve for y, and you get 4 divided by 6 sine of x. Sine inverse of all of that stuff is y. Now bring up Desmos and graph that. So it's y equals cosine inverse of 9 minus 4 cosine x. Y equals arc cosine 9 minus cosine x. But this stuff is all divided by 6. I'll put that inside there. 6. Okay. Why didn't it graph? Did I mess something up? 9 minus 4 cosine x. Oh, this is 4. There we go. I missed out the 4. Yeah. So these are all the possible values of theta 1 and theta 2, or x and y, that would match this equation. Only one of these is going to be useful for me in this physics problem, but I still don't know which one. All of these satisfy this constraint that the horizontal components add up to 9. It's when I involve the other constraint that I can figure out that it's only one theta 1 and theta 2, and that's this second equation. Sine inverse of 4, 6 sine x. y2 equals sine inverse, or arcsine, of 4 divided by 6 times sine x. Now, the only values of x and y, or theta 1 and theta 2, that satisfy both of these constraints is the intersection right here. 0.5601 is x and 0.362 is y, and I'm guessing Desmos, these are in radians. Desmos is displaying these in radians for me. 0.5601 is x. 5601 is x, which I called theta 2. Theta 1 is what I called y, and that is 0.362. And these are radians, so convert back to degrees, and you get 32.1 for theta 2 and 20.7 for theta 1. So if I redraw my diagram, I've got a 9 Newton force to the right. F2 is the 4 Newton force, and theta 2 is the angle that goes with it. That's 32.1. So that is 32.1 degrees. And then the other angle is 20.7 for theta 1. 6 newtons. What did I say? 20.7. 20.7. So to really check, I should see if the components work out here. Do the horizontal components add up to 9? Let me see. That would be 4 times, let me check mode, degree, 4 times cosine 32.1, and then add to that 6 times cosine of 20.7, and I'm going to get 9.00. All right, see, that's some rounding there, but it gave me 9. If I didn't round anywhere in this problem, I'd have 9 exactly. And then I should check that the vertical components actually equal each other. So 4 times the sine of 32.1, that's 2.13. 6 times the sine of 20.7, that's 2.13. 2.12. Again, rounding, but those components equal each other. So the vertical components equal and cancel out. The horizontal components add to 9. That's the actual forces. It's true that I didn't need to do all that to figure out that the net force afterwards was still going to be 9, though. Phew.